Sampling distributions that we will come across quite often in statistics are chi-square, student t distribution, and Fisher F distribution. Today I want to briefly talk about the fundamentals of these distributions. I will not overwhelm you with the proofs and lemmas, but just wanted to give you a very high level picture of the probability density function of these distributions, so that you understand what these are actually when it comes to computation. So forgive me for the writing that I have today, the handwriting. It may not be quite good, and I'm not going to into the details of these distributions proofs, but we'll certainly visit the overall framework of these distributions so that we don't get scared when we face these kind of distributions, and we know exactly what are the mathematical formulas surrounding these distributions. So one of the most important sample statistics which is used to draw conclusion about the population mean is sample mean. So we take the sample mean, and from that we draw the conclusion or the inference about the population mean. So that is where sampling distribution of sample mean is required. Similarly, in the real world, the sampling distributions are never really observed. The process of finding sampling distributions will be very tedious because it will involve very large number of samples. So in real world problems, what we do is we draw a random sample from the population to draw inference about the population parameters. And then a very crucial question arises. Using a random sample of finite size, let us say n, can we make a reliable inference about the population parameter? The answer is yes. Reliable inference about population parameter can be made by using only a finite sample. And this is because of the law of large numbers that we are aware of. So we will go through each of these briefly to understand. And if you remember my previous video, I have shown you the plotting of chi-square. So I'll keep this video very short and restricted to the mathematical part of it without going into the details of the proofs. So if a random sample x1, x2, x3 and up to xn of size n is drawn from a population, let us say a normal population having mean mu and variance sigma squared. So your population has a mean mu and variance sigma square. Then the sample variance, let us say we represent it by s. So we have the formula for the sample variance, which is s square, which is equal to 1 by n minus 1 and summation of the difference of the variable from the sample mean. So that is xi minus x bar whole square. That is the notation part. And here you can see the n minus 1 is the degree of freedom here for the sample. Now subsequently what we are doing here is let me highlight that part so that you will have more clarity on this. So subsequently what we are using in this part, this particular formula is we are just interchanging doing a cross multiplication, and the summation of these squares of the deviations is equal to n minus 1 multiplied by s square. N minus 1, this particular part is the degree of freedom, so which is represented as a nu. So this v, it's not v, it is nu, pronounced as nu. Okay, so nu s square. So what we are saying is we are doing a summation of the squares of the deviation of the sample variable, which is then equal to the variance of the sample multiplied by the degree of freedom. And we then say that there is a variate called chi-square, which is equal to this one divided by the population variance. So the sample variance divided by the population variance multiplied by degree of freedom is the chi-square. Okay, so that is how the chi-square is understood. Fine, and this is the probability density function of chi-square. The PDF for the chi-square is function chi-square is 1 by 2 nu by 2 to the power nu by 2, and here you see we have a gamma function. This is a gamma function. I'll explain you in a few minutes what it is, multiplied by e to the power minus chi-square by 2. The chi-square is the chi-square variate, so we are taking a function on the chi-square variate itself, multiplied by chi-square to the power that nu by 2, the degree of freedom, minus 1, and the degree of freedom is nu, or we say is n minus 1, as we saw in the previous page. And the chi-square variate will vary from 0 to infinity. Okay, so this is the PDF of the chi-square value, and we will see what is the gamma function, so we can relate this probability density function of chi-square. Now in a gamma function, for the derivation of means and variances for T and F distribution, we will use this and this formula. So these are very important formulas. We are not going into the details and proofs. So it says an integration from 0 to infinity x to the power n minus 1 multiplied by e to the power minus x dx is equal to gamma n, and 0 to infinity x to the power n minus 1 e to the power minus ax dx is equal to gamma n by a to the power n, and we subsequently you have a log function, log equation for gamma function. Why it is important, I will show you in few minutes. While we are not going into the details of the gamma and the beta functions, but I thought it is good to show you what gamma and beta functions are, because these are used to calculate the probability density functions of chi-square, T distribution, student distribution, or Fisher distribution. So gamma n plus 1 is equal to n into n gamma, gamma half is equal to root pi, and gamma n is equal to n minus 1 factorial. So that means if I have to take a number, let us say 7, so gamma 7 will be equal to 6 factorial, or you can represent it as a 6 factorial. So it's very simple. Similarly, we have a beta function. So we will be using these two formulas for derivation of the probability density functions. So beta mn, these two numbers m and n, beta mn is equal to gamma m multiplied by gamma n by gamma m plus n, and this is represented as 0 to infinity x to the power m minus 1 divided by 1 plus x to the power m plus n dx, and beta mn is again, this is also represented as 0 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx. The third one is in the trigonometric format, probably will be not using today, but just these two are important and you need to remember it. I'll show you the reference to these functions. Right, so again we have a further gamma beta properties. Beta m1 n1 plus beta n1 m1 is equal to twice beta m1 n1, and subsequently we have the two different, this one and this one, formulas for beta function. Good to know, but we're not going to use it for our today's video. The reason why I'm showing you is beta and gamma functions is because the probability density functions of sampling distributions use these functions. Now coming back to the chi-squared probability density function, so which I showed you already. So this is what is the formula. Once again I'm showing you this particular formula. So this is 1 by 2 to the power degree of freedom nu by 2 gamma nu by 2, now you know what is gamma is, and multiplied by e to the power chi square minus chi square by 2 multiplied by, is again multiplied by chi square to the power nu by 2 minus 1, and chi square is always it varies from 0 to infinity. Okay, so that is how the chi square distribution looks like. We have already seen one plotting in one of our previous videos. Fine. Here we say that if the same example, if a random variable x follows normal distribution with mean mu and variance sigma square, then we know that standard variate, standard normal variate z, that we represent it as x minus mu by sigma, and which is a normal distribution with mean 0 and the variance 1. We have taken one example last time in our expectation and and moments lecture, where I have shown you the expectation and variance of a standard normal variate. So this is how we say that this is this random variable, this one, this is the population mean, and this is the population standard deviation. So to convert it to the standard normal variate, this is standard normal variate we call z, we say x minus mu by sigma becomes equal to a normal distribution with the mean 0 and variance 1. This is a very standard format, right? And the square of the standard normal variate. Now if you take the square of this z, so far z is this one, but if you take the square of z here, this equals, it follows a chi-square distribution with 1 degree of freedom. So when we take the square of the normal variate, that is z square, that is x minus mu by sigma whole square, this will follow a chi-square distribution with degree of freedom 1, which is very important to understand here, right? So if xi are n independent normal variates with mu I, so we have now n independent normal variates with n respective n mu's and variances, also n variances, then the sum of n standard normal variate follows a chi-square distribution. So this is what it means. If xi is follows a distribution with mu I sigma I square, then zi is equal to xi minus mu I by sigma I, it follows. See, this is nothing different. It just says instead of one normal variate, we have multiple normal variates here. So chi square is equal to summation of zi square, and here we say the summation of zi square in this equation also follows the chi square distribution. Okay, and degree of freedom is n here instead of 1, because in the previous we had a case of one variate, we have a multiple n variates. So it is the same thing with the n variates here, right? And this is how a chi square probability distribution function looks like. So this is the chi square. And as you see that if you increase the degree of freedom, the curve shifts towards the skewness or the shifts towards the right side. Okay, fine. Now here comes the usage of knowing the gamma functions and beta functions. So as we know that mu r apostrophe or mu r dash, and in my previous video I have explained in details, that is the moment, r moment about the origin. Now r moment about the origin to find out is equal to, this is obviously the expectation of the chi-square variate to the power r, right? This we have seen in the previous videos. So this is how they do it. 0 to infinity, we integrate the chi-square variate to the power r. F function is the function of chi-square, this is the chi-square is the variate, and d chi-square. And this is subsequently, the whole idea is to write it in this fashion, that is 0 to infinity, integration to infinity is a finite the indication with the limits 0 to infinity, e to the power minus ax, x to the power minus 1 dx. This is equal to gamma n by a to the power n. We saw this formula in our previous slide. So the whole idea is to translate this formula. That's the reason I wanted to show you this formula, the moment, the r moment about the origin. So yes, correct, on the origin to this format, so that we translate the result into this format. You can look at these derivatives, the complexities of these calculations, so the steps which I have omitted in any book in statistics. The idea is to show you how we approach these kind of problems, how we solve these kind of problems, not to give you the complete solution in interest of time. So this is how we derive it using the gamma function. And we have seen in the past videos also that if you put r is equal to 1, that is the first moment about the origin, for r is equal to 1, it is called mean. So the mean comes to be n, and the second moment comes to n into n plus 2. The variance is, as we know, all these things we have already done. We know this formula, variance is equal to the second moment about the origin minus the first moment about the origin square. So it comes to be 2n. So basically what we need to know is the mean is n of a chi-square distribution and the variance is 2n, where n signifies degree of freedom. So this is what I wanted to show you. Okay. Now we talk of another distribution called students t distribution. I'm sorry, I'm quickly going through each of these distributions in the interest of time, just to give you a high level thing, idea of how the distribution looks like and how can we relate it when we try to find out the mean and variances. So here also we say that we take a random sample x1, x2, x3, xn. Again, of size n, same thing, drawn from a normal population with mean mu. So the population mean is always mu and the variance is sigma square. And we know that the sample mean, this is sample mean x bar, is distributed normally with mean mu and variance sigma. This we know, right? This we have seen it. So the sample mean, will be distributed normally with mean mu and variance sigma square by n. Okay. So if the population mean is mu and sigma, sample mean will be distributed normally with mean mu and sigma square by n, where n will be the size of the sample. Okay. This is what is the difference. So here if you see that it's the population, and here if you see that the sample, so both are normally distributed, and the variate z here will be x bar minus mu by sigma by root n is normally distributed with mean 0 and variance 1. So only difference here is we have a sigma by root n, and n signifies the sample size, right? So this is what is the concept. We're not going to prove this, just understand that this is what is the concept. Now in general, that what we know is the sigma is not known. We don't know the standard deviation of the population, right? And so the sample mean as square is used to estimate the population variance. So what we are saying is we don't know the population standard deviation or the population variance, but we can use the sample variance as square, right? So the population variance, we said sigma, this is the population variance, and the sample variance is the sample variance s. So we will use the sample square, population variance sigma square. So we will use the sample variance. We have seen this formula before. F square is equal to 1 by n minus 1 difference of the deviations from the sample mean whole square. In this case, the variate. So this is what is the sample variance. But again, one important thing to note it, in this case the variate x bar minus mu is not normally distributed. So this is not normally distributed. But we see in the previous page, we say that x bar minus mu by sigma by root n right? We say sigma by root n is normally distributed, but here S by root n is not normally distributed, because here in this case, the previous case, the derivations, we have said sigma is always the population standard deviation, right? So here when we give the population parameters, the standard deviation, then it is a normal distribution. But if you give a sample standard deviation, it is not normally distributed, because S will always be positive here. Sample variance will always be positive, whereas sigma cannot be always positive. It can be positive and negative, right? So this will not be a normal distribution and will follow a t distribution or student t distribution. This is important to understand here, with n minus 1 degree of freedom. So t distribution essentially is, this is part is important to understand. T distribution is equal to x bar minus mu divided by s divided by square root of n. Then it resembles a t distribution with a degree of freedom n minus 1. Okay, where s square is equal to 1 by n minus 1 summation I is equal to 1 to n xi minus x bar square, right? So when we put in the variate, when we put the sample variance or the sample deviation, standard deviation, it will not be normally distributed. That is what is important takeaway here. And the PDF of t distribution for nu or n minus 1. So nu is basically the degree of freedom. So if I say if nu is the degree of freedom, then this is the variate can be written. This variate is a t variate, t distribution variate, ft can be represented in this format: 1 divided by square root of mu beta function of 1 to v by 2 1 plus t square by v to the power v plus 1 by 2. And important thing to understand here is, this is very important to understand here, is the limit of the t distribution is from minus infinity to plus infinity. So this is what is the t distribution. Now there is one more t variate which Fisher has given, and Fisher has given another t variate whose PDF distribution or the functions distribution is the same result, but the way it is defined by Fisher for t variate is it is the standard normal variate divided by square root of chi-square variate divided by its degree of freedom. So that means this is standard normal variate, we know is that, which is normally distributed, is seen, and chi-square variate with the n degree of freedom. Now the Fisher's t variate can be represented as t is equal to the standard normal variate divided by square root of chi-square variate divided by its degree of freedom. So z divided by square root of chi-square by n. This can be represented as a Fisher distribution with degree of freedom of n. So this is another way of representing t distribution. And t distribution, as we have seen, is symmetrical about t is equal to 0 because it spans from minus infinity to positive infinity. And you see, if the degree of freedom is more, then it is more, it becomes a more like a normal distribution, and if the degree of freedom is less, then it becomes more flatter, right? So this is all how it looks like. The pictures are not that great, I understand, so I apologize for it. Fine. So since it is symmetric at t is equal to 0, as we have seen, so all moments of odd order are 0. So any distribution which is symmetric, when we say symmetric about 0, is this kind of a distribution is symmetric about 0 is 0. So the odd orders moments will be 0 in these cases, right? So why odd order of moment is important is because we know that the first order of moment about g is equal to mean, so mean will be 0 in a t distribution. And moments of even order, now this is represented as mu apostrophe or mu dash 2r, because a 2r is an even number, 2r plus 1 is an odd number. So this is represented as minus infinity to infinity. So the variate to the power r, or here this is 2r, this is 2r, so it will be 2r ft dt. This is the expectation part, and this is how it is solved. Okay, and we have put the whole function here, and the VDF function which I showed you, and then it is further derived. Okay, so upon solving, we are not going to the steps of the solving these equations. So this is the, after you solve it, the values they come in the either in terms of n or r, right? And this is a gamma function, and n is greater than 2r obviously. So we get when we put r is equal to 1, so we get the second order of moment about the origin, mu2 apostrophe from mu2 dash is equal to n by n minus 2, and this has to be for n is equal to greater than 2, because if it is less than 2 or 2, then this is less than 2 is it will become a problem, it will become negative, and for greater than 2 it will become, and equal to 2 it will become 0. So it has to be greater than 1 by n by 0 infinite, so it's not derivable. So it has to be more than 2, and the variance is equal to, you know, the same formula. So variance is n by n minus 2, right? So mean is 0 and variance is n by n minus 2. In this case, let us go to other one. So for F distribution, for Fisher distribution, we saw that chi squared is equal to the degree of freedom samples, and that is the variance of the sample divided by the variance of the population into multiplied by degree of freedom. It's a chi square distribution with the degree of freedom mu, right? This is the degree of freedom mu, this is the chi square degree of freedom. Now we will use this to understand the Fisher distribution. So let us say we have two samples from two populations, right? From two different populations. One is x1, x2 up to xn. We are taking this sample from population 1 with mean mu1 and value sigma 1, and we are using another y1, y2, yn from population 2 with mean mu2 and variance sigma 2 square. Okay, we are taking samples x1 to xn from population 1 and y1 to yn from population 2, and we will use this particular distribution formula to further understand the Fisher distribution. So for this is for the chi1 square, for the chi square variate 1 for population 1, this is what it is. It is mu1 is the degree of freedom for the population, the sample from which the first sample, S1 is the standard deviation of sample 1, sigma 1 is the population standard deviation. This is how we can represent, right? Similarly for the second variate, for the second sample, this is how we can write equal to chi square. The same thing, we are just replacing nu with mu1, nu with mu2, S1 here, S2 here, sigma 1 here, sigma 2 here, right? The idea is to come to this ratio, chi1 square divided by chi2 square. So this is the chi square variate for sample 1, chi square variate for sample 2, okay, is equal to this thing, mu1 S1 square divided by sigma 1 square whole divided by mu2 S2 square divided by sigma 2 square. So ultimately we arrive at this one. So this, the sample variance by population variance divided by the sample variance by population variance for the sample is equal to the chi square variate divided by degree of freedom for the first sample, the chi square variate from second sample, and this follows a Fisher distribution with mu1 and mu2 degree of freedom. Okay. So the ratio of two independent chi-square variates when divided by their respective degrees of freedom follows F distribution. This is what we have seen. Ratio of two independent variates when these are two independent chi-square variate divided by their degree of freedom follows F distribution. This is what I wanted to show you as a takeaway. Now in this case, if sigma 1 and sigma 2, the population variances of population 1 and 2 are same, then F distribution will be equal to the sample variance, the ratio of the sample variance. So that is very important to understand. So if the two populations have the same variances, then F distribution will be a ratio of the two sample variances with the degree of freedom mu1 mu2. Okay, this may not sound very interesting now, could be a little bit of a dry subject, but you will understand how to relate these concepts when you solve more complex problems on sampling distribution, estimations, and statistical inference. So these are very important to understand at least. So the probability density function of F distribution here again can be represented in this notation. Here we are using a beta function. So this is the Fisher variate mu1 by mu2 to the power mu1 by 2. This is the Fisher variate F to the power mu1 by 2 minus 1, and beta function mu1 by 2 mu2 by 2 multiplied by 1 plus mu1 by mu2 F to the power mu1 plus mu2 by 2, and F will be here again from 0 to infinity. Okay, so the mean of the F distribution we calculate as this. The mean is mu2 by mu2 minus 2. So that is the importance of this derivative, or this value, is that the mean is independent of the first degree of freedom. So it is only the mu2, the mu1 is missing here, so mu2 by mu2 minus 2, and this is obviously for mu2 greater than 2 here. Variance will be 2 mu2 square multiplied by mu1 plus mu2 minus 2 divided by mu1 multiplied by mu2 minus 2 whole square multiplied by mu2 minus 4, and this is again for mu2 greater than 4. One important thing when you solve the problems and statistics, is very important in F distribution to understand, is the interchanging degrees of freedom mu1 and mu2. I will show you one example. As of now, just understand that the Fisher F variate with distribution mu1 mu2 for mu1 and mu2 degree of freedom, and 1 minus alpha is equal to reciprocal of 1 by F mu2 by mu1. So here these are interchanged, so mu2 goes here and this comes here. So we are just interchanging the degrees of freedom, here the orders, and here is alpha, which is 1 minus alpha, the reciprocal of F mu2 mu1 alpha. I'll show you one simple example what it means. And this is how the F distribution looks like. This is a skewed distribution, it's not a symmetrical, and again this graph is obviously not the best graph that you can see. Just wanted to show you how the distribution looks like. And as I said, I'll show you one example, a very short example, so that you can understand what the reciprocal of F that I showed you earlier. So this is the F distribution, this is the variate F for mu1 mu2, and this is alpha is the area, the upper tail area we call it, the darkened area, the dark blue area is the alpha area. So for all these distributions you have tables, chi-square, student table, T distribution, F distribution. So for F distribution you will have 2 degrees of freedom, mu1 and mu2. So suppose there is a question to find the value of F variate. Okay, now they say the question is find the F variate for alpha is equal to 0.95 and the degree of freedom mu1 and 2 given as 12 and 16. So if you see the F distribution tables, you will have alpha values for these 0.1, 0.05, 0.25, 0.01, 1025, 0.01, but we don't have alpha values for 0.9. So we know that 0.95 is equal to 1 minus 0.05, right? So you use so for alpha variate of nu1, nu2, 1 minus alpha is equal to 1 by f nu2 nu1 alpha. So for f variate, we have to find the value of the Fisher variate for degree of freedom 12 and 16, and alpha is 0.95 is as good as 1 by Fisher variate for degree of freedom 16 and 12, and this is their alpha. So if I say 1 minus alpha is equal to 0.95, then alpha will be equal to 1 minus 0.95, that is equal to 0.05. So in the table you see the value of Fisher variate for 0.05 with the degree of freedom nu1 as 16 and nu2 as 12, just the reverse order, and that is how you solve it. So that property is very, very important. Okay, this is an optional slide I thought I will show you for calculating the moments of F distribution. The reason I kept it optional is because this is complicated calculation, and you can practice yourself. It uses the beta and gamma functions. Anyway, this one. Okay, so again the moment of order r about the origin is E of r. We know this, 0 to infinity integration f to the power r is the Fisher variate to the power r f is the Fisher variate df. So this is again Fisher variate. Now we have put the probability density function here of Fisher variate, which we saw earlier, right? Fisher distribution. I'll show you the probability density function of Fisher distribution. This is the Fisher distribution probability density function. 1 minute. This is the one. So we have put this here, and to solve it, you have taken nu1 by nu2, f is equal to x. So this is the way to solve this. Something you can try yourself, and then to reduce it in terms of x, and again the same equation we rewrite. When you put this in term x, then you do df dx, and you convert this into this format. The idea is to convert it into a standard beta function. So this is the standard beta function. If you see this one, let me show you this particular function. This is a standard beta function which we saw in one of our page or slide. The whole idea is to convert it in this format. So we converted it into this format, so that this is the final format we converted it. So here you will see the beta function nu1 by 2 plus r, nu2 by 2 minus r. Do not get overwhelmed. You have to try it. Is a bit tricky. I'm not gone into the details of these calculations. So just to show you why beta functions, the standard beta functions and top functions, the formulas are important. So finally, this comes. This is the final value of the moment, r moment about the origin, which is represented in terms of the degrees of freedom and r, right? So mean, as we already saw, for this is equal to the first order moment about origin. It comes out to be v2 by v2 minus 2, and v2 is greater than 2, and as I told you that is independent of this is not, I mean, nu2 by nu2 minus 2, as I showed, is independent of nu1, so independent of the first degree of freedom, and this is the second order moment about the origin, this value, and the variance is the same thing that I showed you in one of the previous page. So this is the final variance. Now these are complex calculations. I have not gone into the step-by-step calculations, because that is not the idea. The idea is was to show you what are these probability distribution function, density functions, and how we derive it using beta and gamma functions. We have not gone into the details of beta and gamma functions as well. I've just shown you the high level skeleton of beta and gamma functions. So these are the functions that you should understand. You should know these functions. Unless you know these functions, you will not be able to solve these kind of problems. So it's the gamma function. These first two functions we have used. Is the beta function, first two functions we have used. So to calculate the moment about the origin for student and Fisher distribution, these two functions are enough for you. These two formulas are enough for you. 2 in the gamma and 2 in the beta. That is enough for you. So thanks for watching this video. I know this is a dull video, so complete calculations, but I thought is important for any student of statistics or any professional who wants to understand these distributions from a mathematical perspective. And later on we will solve these estimations and other statistical inference questions using these distributions. But it is good to know the framework of these distributions and how their moments look like, what's the mean and what's the variance and how it looks like. So thank you for watching this video, and thanks once again. I hope you liked it. Thank you. Bye.